Okay, I'm going to talk today about probing one-dimensional superlattices at the LAO STO interface. And the motivation for the work I'm going to show you today is to try and develop the use of a solid-state system to perform quantum simulation. So just a brief background on quantum simulation. There's an extensive amount of work that's been done in the field using cold atoms. So pictured here you have magnetic and optical traps, which can be used to create a lattice of sites and then trap and control a large number of atoms at specific sites. And so the external fields can then be used to control the interactions of the atoms, and this allows for the creation of strongly correlated systems and the ability to realize a wide range of many-body Hamiltonians. And so experimentally here, you can see they really do have site-level control in the lattice. And they can simulate strongly interacting systems, which are described by Hubbard-type lattice models. And this allows them to gain experimental insight into phase diagrams of systems which are difficult or impossible to model classically, such as the two-dimensional Hubbard model, which may give insight into the high-temperature superconductivity. So again, they have this system, and the Hamiltonian are extremely well understood. It can be very precisely controlled. It is, however, difficult for them to reach low effective temperatures where correlated ground states occur. And so one possible alternative is that instead of using cold atoms to simulate these systems that appear in solid-state physics, what if instead we use a solid-state platform that could naturally support the physics we wish to study to do this quantum simulation, where it is easier to reach low effective temperatures where complex quantum phase diagrams such as magnetic phases, pseudogap phases, or even superconductivity could be studied. And so one potential candidate for such a solid-state quantum simulation platform is LAO STO. So I think most people here are familiar with the system, but essentially we have the interface which exhibits very rich and interesting physics, including nearly every major phenomena in the solid state. We think this makes this a very interesting candidate for a solid-state quantum simulation platform. And so the work I'm going to show you today is based on nanoscale patterning of this interface using conductive AFM lithography. So we start with 3-unit cell LAO STO, so the interface is naturally insulating. And then we can etch away the top surface and deposit titanium gold to make contact to the interface of the material. And then if we bring a conductive AFM tip in contact with the surface of the material and apply a positive voltage and then move it across the surface, we can deposit protons on the surface, which will attract electrons to the interface and essentially create conducting channels or nanowires at the interface of the material. And these nanowires can be as small as 2 nanometers. And so this positive voltages on the AFM tip will write these channels, and then we can apply a negative voltage to the tip to selectively erase them and create barriers, which allows for the creation of some very interesting devices. So for example, we can create single electron transistors where we have a 1.5 nanometer conducting island at the interface, which can then be controlled using gates, which are also defined using conductive AFM lithography. And so this is essentially a solid-state atom and can potentially be used as a building block for making quantum materials. So we can also create devices which exhibit electron pairing without superconductivity. So here you have a state here with paired electrons, and then as you increase the magnetic field, these split into single electron states. And this splitting happens at a magnetic field much higher than the critical field for superconductivity, and this indicates that we have strongly attractive electron-electron interactions in these devices. We can also create electron waveguide devices where a constriction in the wire allows us to control the number of quantum channels. So as we tune a psi-gate voltage, or essentially tune the chemical potential in the device, we see the conductance increase in steps of E squared over H, indicating that we have very clean ballistic transport. And finally, we can create devices where we see tunable electron-electron interactions. So using a gate, we can tune a transition from pair tunneling or attractive interactions to single electron tunneling or repulsive interactions, just by tuning the chemical potential of the device. So here we exhibit all of the ingredients that we would need for quantum simulation, including strong, controllable, sign-changing electron-electron interactions and the ability to reconfigure the device on the nanoscale. So we're going to try and use these techniques to develop a solid-state quantum simulation platform. So the typical density of the interface is 10 to the 13 per centimeter squared, which corresponds to about 1 electron every 3 nanometers. So using this technique, we really have control on the scale where we have 1 electron per smallest feature that we can create. And this allows us to create a lattice of sites for putting electrons which doesn't have to bear any resemblance to the underlying lattice of the LAO STO. And in this way, we can create any number of one-dimensional or two-dimensional lattices and simulate a wide range of Hamiltonians, such as the Hubbard model Hamiltonian pictured here. So again, we take this unperturbed interface, which is naturally superconducting, and then we can perturb it by adding this nanoscale patterning and perhaps undergo quantum phase transitions into new states. So here you see Feynman dreaming about this idea of quantum simulation. And so we've begun our work by focusing in one dimension because it's more theoretically tractable. So now let me try and describe the devices that we've been creating. So they're one-dimensional superlattice devices. So they're created by using the AFM tip. So we write a nanowire at the interface and then use the AFM tip to, as we're moving across this wire, apply a series of negative voltage pulses to the tip. And so this creates a series of barriers in the wire, or a one-dimensional chain of conducting islands at this interface. And so this is incorporated with an electron waveguide in order to probe the device with very clean transport. And so these devices are written at room temperature in the AFM and then placed in a dilution refrigerator where they're cooled to millikelvin temperatures, and we can perform magnetotransport measurements. And so we can apply an out-of-plane magnetic field and then also tune the chemical potential of the device by applying a voltage to a local side gate, which is also created using this conductive AFM lithography. So let me first show you the control device, which is just an electron waveguide device. So as you can see here, you have you see the conductance. Each curve is at a different magnetic field, and as you increase the gate voltage, you see the conductance increase in steps of 2e squared over h. And so this color plot up here is of the transconductance. So you have the derivative of these curves with respect to gate voltage. So the dark regions here are on the plateaus where the derivative is 0, and then the bright regions are transitioning between plateaus. And so we see we have this map of the transconductance as we change magnetic field and the side gate voltage. So that's for the control device. And then when we add the superlattice in series with the electron waveguide, we see something very different. So again, you see conductance as a function of gate voltage and then this transconductance map. And the magnetotransport revealed through this transconductance, which can be interpreted as a local density of states, exhibits a complex manifold of states which are not present in the control device. So due to the superlattice here in these states, most of these states here actually correspond to conductance plateaus, which are at half integer values of e squared over h. So we're seeing some very interesting states here in these devices due to this superlattice. So here are just a few more superlattice devices. So again, here these transconductance maps reveal the local density of states in these devices, and so it's clear basically the devices are not reproducible, so we don't have the ability to make these devices on demand. And so what we're working on right now is improving the control that we have over them, over the chemical potential to potentially hopefully find the regime where these superlattice features are more prevalent. And so again, we see this complex manifold of states in these devices. And actually there's one more interesting feature in this last one. It actually has plateaus, this first plateau at 0.5 e²/h. So again, we're seeing signatures of perhaps half-integer charge objects in these devices. So it's even more clear if you look at this Ivy curve spectroscopy. Again, on the left we have a control device. So at 0 bias we see the conductance increase in steps of 1 e²/h, and then at this finite bias on this triangle we see the half-integer plateaus, which basically indicates that we have very clean transport. And then in this superlattice device at 0 bias we have steps of 0.5 e²/h, and then at finite bias the first is actually at 0.25. So we have this very clean transport, and perhaps these interesting new states from this superlattice, which we'll continue to study. So in summary, we have been trying to develop a platform for solid-state quantum simulation, and we have all of the ingredients that we should need at this LAO-STO interface. And we've been begun by trying to create one-dimensional superlattice devices at the interface.